For this module, I'll be going over the general linear model, analysis of variances, or ANOVA, and multiple regression correlation, or MRC. My hypothesis is interrogating social motivation and its potential to modulate reward-seeking behavior in autism spectrum disorders. The general linear model is an additive that posits that both our x and y's are linear and that there is no multicollinearity, that the average model error is equal to 0, and that there's no autocorrelations and all of our models are normally distributed. Both multiple regression and analysis of variance, or ANOVA, uses the general linear model equation. This equation is y is the phenomena of interest, or our dependent variable, is equal to b naught, which is the intercept or the y value of all independent variables, plus bx, which in multiple regression is all the covariates in the model, and in ANOVA it is all the nominal factors at those, that is the class level variables, and it would be an analysis of variance. And then plus E in ANOVA, E stands for error. This is from the Platonic essentialism, the essence that perfection exists. So everything, every residual is classified as error in ANOVA, and it stays as residuals in multiple regression. Here is my data set for Module 3. As you can see, we have 3 different types of variables. We have 4 independent variables measured in y. We have 7 dependent variables measured in x. And we have 8 class level nominal variables, and those are from factor 1 to factor 8. I will use this data set. Of note, y4 looks extremely inappropriate for this data set and possibly could violate our assumptions about the general linear model, and I'm going to further investigate that in the next few slides. Here we have a nice correlation matrix of all the independent variables we are concerned about in tabular form, and you can see that of note, y1 and y3 have a strong interaction effect. And so to check and make sure that the multicollinearity is not inflating our results, we run a variance or variable inflation factor analysis. This estimates how much the variance of each regression coefficient is inflated due to multicollinearity. And variables that have an inflation factor of 5 it would meet the criteria that we would say there's a violation of assumption. However, none of our variables reach the level of 5, so we can suggest that there's no violation of assumption that multicollinearity is highly inflating our results. Here we ran a simple regression model that looks at the interaction between y1 and the other 3 independent variables, y2, y3, and y4. All interactions are a measurement of residuals. In this case, it is the estimate divided by the standard error, so what we expect divided by the residuals give us our t-value. Of note, y3 has a much stronger interaction effect with y1 than it does on its own. This is a violation of the general linear model. It violates that there's no multicollinearity. It violates that there's no errors of omission or measurement. And it violates that there's normally distributed errors. We are only concerned in this module about main effects and not the significance of interactions between two variables. So I'll talk about more about the main effects in the next couple slides. The general linear model posits that all of our residuals add up and equal to 0 in a perfect model. As you can see, we do not have that, and so thus we don't have homoscedasticity. We used a low S-curve line. As you can see, it is not perfectly straight, and also it fluctuates based on each data point that regresses from this mean. So this is an interpretation that we can make to say and argue for that we violated the assumption of the general linear model in this case also, and this is reflective of that. Also, in the general linear model, or GLM, we expect to have a nice bell curve of evenly normally distributed data points. However, this histogram shows that our residuals are unbalanced and not normally distributed. Here are QQ plots that tell us how much the data points spread between residuals of each data point. And I want to focus on the bottom right graph because that shows Cook's distance, and Cook's distance is a good measurement tool used to tell us where it would be good to where in the graph it would be good to collect more data points so that our line could be more homoscedastic and more fit the GLM model. In addition, Cook's distance also has the ability to indicate influential data points that might be or outliers that might be driving up the mean or the difference in means that we see in our data set. Or it can indicate, like I said previously, regions in space where it'd be good to add more data points so the line has more homoscedasticity. Here I wanted to revisit these slides to really drive the point home. So our variables of interest, in particular Y1, which is social motivation, and Y3, which is reward-seeking behavior. Those two, when they interact, have a much stronger effect than when they stand alone. And if you can see the probability of T, this tells us that there's a difference in social motivation and reward seeking, that the difference is very low if the null is true. And so we were able to reject the null hypothesis. As Cortina states in her paper 2002, you either reject the null hypothesis or you fail to reject the null hypothesis. You don't accept the null hypothesis. So this interaction between Y1, social motivation, and Y3, reward-seeking behavior, is beyond what we would expect from the main effects of them standing alone. Thus, their combination in the interaction between social motivation and reward-seeking behavior is much greater than what you would expect from social motivation alone and reward-seeking behavior alone.